To lift a fully loaded 400,000-pound commercial airliner off the tarmac, you need an extraordinary amount of upward and forward force. Newton's third law tells us that every action has an equal and opposite reaction. To push an aircraft of that massive size forward, the propulsion system has to grab a massive amount of weight from the surrounding air and accelerate it violently backward. For decades, aviation relied on the traditional piston engine. These internal combustion engines operate in distinct, successive steps, taking air in, then compressing it, igniting it to create power, and exhausting it out the back. Scaling up that stop-and-go process to move larger aircraft requires incredibly bulky mechanics. You end up with a dense web of heavy steel cylinders and pushrods that add immense weight to the plane, limiting how much it can carry. To achieve the speeds and lift necessary for modern commercial flight, aircraft cannot rely on interrupted, successive cycles. They require a machine capable of generating power simultaneously and continuously. That specific physical requirement gave rise to the modern high-bypass turbofan, the mechanical marvel that powers nearly all commercial flight today. Its defining advantage is that it never waits for one cycle to finish before starting the next. It performs intake, compression, combustion, and exhaust all at the exact same time in different sections of the engine. Instead of drawing air in quick gulps, the turbofan acts as a vacuum, inhaling an endless, violent tornado of air into its massive front intake. To extract maximum efficiency, the engine immediately takes that massive volume of continuous air and splits it down two completely different functional paths. The moment the air enters the engine housing, it slams into a set of spinning titanium fan blades at the front. This initiates what engineers call the Great Split. A small fraction of the incoming air is sucked directly into the center core of the engine, while the vast majority is routed around the outside of that core. The ratio of air going around the core compared to the air going through it is known as the bypass ratio. By acting almost like a highly efficient ducted propeller, this outer fan captures huge volumes of air and accelerates it backward. This bypass air is much cooler and moves slower than the ignited exhaust from the core. Yet because of its sheer volume, its momentum generates the vast majority of the airplane's forward thrust. Routing air this way keeps the flight quiet and highly fuel efficient. However, spinning a front fan of that size against the atmosphere requires an immense independent power source, which sits inside the engine's core. To understand where that driving power comes from, we must look at the small percentage of air that actually entered the center of the engine. This air enters a continuous thermodynamic loop known as the Brayton cycle, designed specifically to extract mechanical energy from a fluid. This chart visualizes the phases of the Brayton cycle, starting with the compressor. As the air passes through consecutive rings of shrinking blades, it gets squeezed tightly into a narrowing channel, causing its pressure and temperature to rapidly spike. In the combustion phase, flammable aviation fuel is sprayed directly into this highly pressurized air and ignited. This creates a continuous explosion of rapidly expanding high-energy gases that rush backward, forcing their way through a series of rear turbine blades. This continuous sequence of squeezing, igniting, and expanding produces a stream of high-velocity exhaust that is entirely dedicated to performing mechanical work. The mechanical genius of the turbofan lies in what those rear turbine blades are attached to. They connect via a central rotating shaft that runs all the way back up to the front compressor and the massive bypass fan. By utilizing advanced material science to protect the engine's internal structure, engineers can push the thermodynamic limits of the Brayton cycle, running the core hotter to extract the maximum possible efficiency. Zooming out, the entire turbofan operates as a single harmonious unit. The violent, explosive power of the hot inner core exists to seamlessly drive the cool, massive, and highly efficient bypass fan at the front. The modern high-bypass turbofan represents an absolute mastery of thermodynamics and fluid dynamics, engineered specifically to sustain heavy, continuous thrust over thousands of miles. It's a mechanical reality you can actually feel as you sit on a runway waiting for takeoff, listening to that low, steadily rising hum. That sound is a self-sustaining, carefully contained tornado of physics, spooling up to safely propel humanity across the sky.